What's up guys, Shawnthebro here, and we're back for another episode of the fighting game tutorial series, and specifically our 3D fighter. So we have our fighting game tutorial series, and that is a 2D and 2.5D, and then we have this mini series for our 3D fighter. To this point we have tackled several concepts for the 3D fighter. Specifically, we have our 3D boundaries, so we can only move to certain points both left and right and forward and backward. We also have 3D orbiting movement and facing the character in 3D space. We have a way to enable this, so cheat enable 3D mode, true. And when I do this, it does turn that character around. Otherwise, it is going to be three-dimensional. So I can move in space, and you'll see that I can orbit around the character. You see the map behind it. And we can still move left and right like normal. Now, something you'll see that we have now that we didn't have before is a 3D camera. So before we were orbiting the characters and we would see the character leave the camera view, but now we have the camera rotating around to the midpoint between the two characters. This works regardless of where we are distance wise. So we can move along this path and then rotate wherever we want, and the camera will stay. At this point we can bring it all together and have a pretty functional 3D fighter. Even our hitboxes are working in 3D as far as spawning them. All the collisions not set up yet, but it will be shortly. Now this camera is very precise. It's not really smooth like you would typically see. That is a simple change. If you've been watching the series, you'll know that we've set up that sort of thing on some of our other cameras. That's something we'll set up in another episode or later in this episode if there is extra time. But as long as we have the orbit movement down, making it smooth or take some time to adjust is very simple. Now, some movement in the 3D fighter is a little awkward, just from a few things that we haven't tackled yet. So when we try and jump over the character, we may not be able to. We'll do this sort of like deflection that you're seeing right there. And so we can't really test jumping over the character yet. But don't worry, this is all coming soon. These are all known issues and known things that we need to implement. Now, before we hop into this episode, if you want to get caught up in the series and check out everything we've done in the Fighting Game tutorial series, from our hitboxes, our health bar, our game mode, our different attacks, and a whole lot more, I'll link you to the entire Fighting Game tutorial series right here in the top right corner, and you can check out how we did all of that. Alternatively, if you don't care about that and you only care about the 3D fighter, I will link you to the first episode of the 3D fighter conversion mini-series. As even though this camera episode can be followed without following the rest of this series, I do recommend that you watch those other episodes so that you're familiar with why we're doing what we're doing and why it works the way it does. With that out of the way, we can go ahead and get started. Now, this is a code and blueprint tutorial series. We're going to be doing everything in code today because we recently converted our camera from blueprint to code, and we're going to be editing that file. So if we go into Visual Studio, or our IDE of choice, and we go down to our tick function in our base camera. This is the function we were previously using for our 2D camera, and it still functions perfectly fine for two-dimensional space, and we could modify it for 3D space, but I wanted to make a new function for this so that we could show you exactly what we need to do to make this camera. This is 2D and 3D supported. It works for both. And it's not really complicated compared to this one. This one actually has a little bit more just because of the way I set it up. So what I literally did for this was copy this entire function that we had created. If you haven't been following the camera episodes, you won't have this, but the very simple explanation for what's going on here is we have a camera and tick updates every frame. We check and make sure that we can get our game mode because our game mode has our characters, and we make sure that we have two different characters to use this camera this way. Then if we do, we get the camera X location because our camera X wasn't changing. In the 2 and 2.5D version of the fighter, we can't move on the X axis. So the camera doesn't need to move on the X axis either. Maybe for special moves and things, but those are handled separately. So as far as the fight camera goes, we do not need to move it on the X axis. And because of that, I was flat out ignoring the x-axis in a lot of sections, like in the sum of the characters and the average distance, or the midpoints between the characters. So you see here I had some y and some z, and average y and average z, but we did not have some x and average x. Then we were checking to see if we set the camera bounds already, and if we didn't, we were setting the minimum camera height to that. We want to have the height modified with the character's height, so if the characters are jumping, it will move up to meet the midpoint of the height or the z-axis. Then we were determining if the camera should move and passing in the average Y location. So we had to check to see if the new camera location was going to go outside the boundaries of the left or right side. And as long as we're in a valid spot, we were going to move the camera. We were calculating the new location based off the camera X, the average Y axis of the characters, or the midpoint, or the height based off what I was mentioning earlier with the average Z and the min camera height and a max camera height that we set in the header file. Once we had the location, we were setting it. And then we were moving the camera boundaries or the stage boundaries at this point, because based on where the camera is and where the distance between the characters was changing, we were also moving those inner boundaries. Then the else, if we shouldn't move the camera because it was going to be out of bounds, we were setting it to a default location on the X and Y, so basically keeping it where it was and then only modifying height at that point. Then we were setting the actor location. Lastly, we were adjusting the field of view of the camera by getting the distance between the characters and then multiplying that by the field of view modifier, which is basically just how we want it to look, how far away we want it to be. And we were clamping that between a min and max field of view so we couldn't get too far out or too close. Once we had all that set up, we set the field of view on the camera. So now if we go up here to our new version of the function, we have void a base camera : tick float delta time and super : tick delta time. These are the same things as before. We're going to call the function. It's going to update every frame, and it's going to call the super or the parent's tick, which is a camera actor. Then we still do the same checks that we did in our other function as well. We check to see if we have the game mode by casting get world get auth game mode from Unreal to our game mode type, which is a fighter template game mode, and setting it to this variable. Here we check to see if we have two characters, and since this series supports tag matches, we have to check active team 1 character and active team 2 character. But if both these are valid, then we have all the information we need to create our 3D camera. So from here, we're still going to do the same first step as we were doing before, where we were getting the sums of the character locations. Except this time we care about X, Y, and Z. So instead of splitting it up into some X, some Y, some Z, we're going to make F vector, some location, and set it equal to base game mode, active team 1 character, get actor location, plus base game mode, active team 2 character, get active location. So we're flat out just adding these vectors together at this point, or adding their locations together at this point. And the next step is also the same. We need to determine the average location of the characters. So we were doing this before, but it was average Y and average Z. This time it's going to be average location. So F vector, average location, and it equals some location times 0.5F. Now what's different about this function, and this is one of the most important parts, is the direction that we want to face the camera. So when we look at our old function, we knew we were facing the camera on the x-axis just at camera X and at average Y and at the height determined here. But it's not as simple this time. This time we have to determine where we want to rotate the camera to and place it there. We can do this by determining the direction between the characters. So if you were to draw a line from one character to the other character, that is your direction of fight, or your direction vector between those characters. And if you're not familiar with direction vectors, it's okay, but essentially all it is a vector, right? 3 values, X, Y, and Z, that represent a line drawn between the characters. So I'm calling this the character direction. A very simple way to do this is to make a variable f vector, character direction, and set it equal to the difference in the actor locations. This is basically the distance between them, right? We're subtracting these values. So base game mode active team 1 character, get actor location, minus base game mode active team 2 character, get actor location. And this is in parentheses because this whole operation has get safe normal 2D function called on it. If you're not familiar with normals, a very good example that was told to me that always sticks with me is, imagine you have a paper and imagine you have a pencil, and you want to stick that pencil directly through the center of the paper. Your paper is your plane and your pencil is your point, so your pencil is pointing directly at your paper. This represents your normal. So if I pull up paint here and we draw a plane, imagine this is a perfect square, this is your paper, or perfect rectangle, right? And you have an arrow pointing directly in the center of this. So that the arrow is 90 degrees or orthogonal to the paper. Then that is your normal. If your paper is rotated like this, then your arrow is going to rotate so that it still hits in the center of the paper like that. And this is really the same idea with our camera. So we want to point the arrow. So we want to know the fight direction. That is really our plane or our paper in the example I was just showing. The way the characters can have a line drawn through them and you get your direction vector, that is our direction of fight. But the camera is positioned looking at the characters so it can see them both. So from the character on the left, it's 90 degrees to their right. From the character on the right, it's 90 degrees to their left. So this gets us the direction of fight, and then we need the camera direction as well. And the camera direction is F vector camera direction equals F vector : cross product. We're going to use the F vector up vector and our negative character direction. I was showing you what a normal was, right? But say we have this paper again. In this case, this is going to be our screen. So say this is our viewport. And then we have our up vector here. This is up from our world. Then we have our fight direction, which is the way the characters are facing each other. The cross product in this case is going to be the vector that is perpendicular to both of these vectors. So if we have our up vector and we have our fight vector, then the cross product is actually going to be right at the camera and we'll go here. It's kind of hard to draw it in that case, but again, if we put this at an angle, for example, and we have our up vector, then we have our fight direction vector, then our camera vector should be going directly to the center of those points, but perpendicular. It should be coming straight out. So the tail of this one, or the line from this arrow, would point directly at the camera. And that's good, because if this is our fighting direction and this is our up direction, then this is where our camera should be. That's what cross product will give us. So we use the up vector because that one we know for sure is not going to change, and then we use our character direction or our fight direction vector or whatever we're calling this, and that will get us our cross product. But the thing is, we want to use negative character direction in this case if we want the camera to be on the right side of the left player and the left side of the right player, like 3D fighters typically are. Basically, it'll keep the same sides as our 2 and 2.5D fighter. If you use positive character direction here, you'll just be on the other side. You'll be flipped. So player 1 would be the character on the right, and player 2 would be your character on the left. So it would just be opposite of what you're used to seeing. Then we get the safe normal from that, which is just the direction vector. Again, we don't need all these specific values. We just want to get the normal of it because we need to know the direction vector of the camera. Once we have the character direction vector and the camera direction vector, then we can calculate the actual location. That means at this point we're ready to move the camera. So just like in the old session for this, we had F vector calculated location equals F vector, and we were passing in some values that we had determined earlier. We're doing the same thing. We're going to pass in different values, but it is the exact same step. So F vector calculated location is going to equal the average location of the characters. So essentially the midpoint of the characters, but we also want to apply the offset of where we want the camera to be. If the camera is directly at the midpoint of the characters, it's going to be way too close. You're not going to be able to see either of the characters. So we want to take the camera direction vector, which will be oriented at that exact spot, that midpoint, and we want to multiply it by our offset x-axis. This is a variable we set up in the regular camera, but it is the x distance that we want from the characters. Since we are moving this camera and also rotating it to face that midpoint, we still need to have an offset from it to move it away from the character so it can see everything that's going on in the world. Offset x-axis is set up here at 550 units, or 550 centimeters in this case. And so we're going to take the midpoint or the average location, we're going to take the camera vector and multiply it by that 550, or whatever value you have yours set to if you changed it, and that's going to be our new calculated location. Also, like in the previous implementation, we're just going to call set actor location, passing in calculated location now. And then this line is exactly the same as in the previous implementation. We are going to call calculate inner boundaries and pass in is team 1 character on left. Then we need to rotate the camera because unlike with the 2D version where we just set the location and then we set the field of view, since we are orbiting around the characters here, our location could be wrong. We could have that offset, but we might be oriented a different way. We want to make sure we're constantly rotating to meet that midpoint. So we need our rotation that we want to use for our camera. So it's F rotator, and I call it camera midpoint rotation. And it's just going to be the difference between our average location and our calculated location. Because remember, we have our average location, which is our midpoint of our characters, and then we have our calculated location, which is that offset by how far back we want the camera at. And we're just going to get the rotation of that. There is an f vector function to do so you can just put this in parentheses and do dot rotation. And this will determine where that difference in vectors points, where that direction is for that vector. And that's the rotation we want because we just want to point the camera at that rotation. So set actor rotation, camera midpoint rotation. And now this will rotate the camera correctly. At the last point, we have to modify the field of view of the camera. And we're going to do that here the same way that we did it in the 2D version. Only difference is we're not only accounting for the y-axis now, or the z-axis even. When we're doing float distance, it's not float dist y anymore like it was before. It's just the whole distance. And we need the distance between the entire vector, not just the y-axis. So f vector : dist to get the distance between two vectors. This will be the x, y, and z axes. And we need to pass in the active team 1 character location and the active team 2 character location. Once we have the distance, it is basically the same logic as before. We set our current field of view variable that we have equal to fmath : clamp, so that we give it a minimum and a maximum that it can reach. Then we get the absolute value of distance, which is this variable here, times our field of view modifier. This is the same modifier we were using in the 2D version. I believe this is 0.12f. It is. Then I'm still using min field of view and max field of view for the clamp, so we can't go below this number or above this number. And my numbers are 45 and 85. Once we have our current field of view, we want to set the field of view of the camera. So this is a camera actor, and that means we have a camera component, so we can get camera component set field of view with current field of view. It's the same way we were doing it in the 2 and 2.5D camera as well. At this point, you can go ahead and launch your game and test out the results. I hope you guys enjoyed this episode of the 3D fighting game camera, and if you did, please subscribe and consider joining the Patreon, YouTube membership, and Discord subscriptions for more benefits. Thank you so much to everyone who has. I'm incredibly grateful for all the love and support. If you ran into any problems following this tutorial or any of my tutorials, feel free to join the Discord community. There is a link in the description, and I would be happy to help you out. Thank you so much for watching. I'm Shawnthebro, and I'll see you in the next one. Goodbye, guys.